We'll talk about three major trends that we see in the data landscape today. And I'll briefly introduce E6 Data's bet, how we are thinking about navigating these three trends. Our mission is to unlock the full potential of data, analytics, and AI through next generation of compute efficiency and intelligence. We see a huge explosion in the need for compute. And we believe that to address the upcoming need, we need to rethink how compute is surfaced. Why do we have this exponential demand for compute? On one hand, we have a huge change in data footprint. One reason, of course, is a lot of structured and unstructured data. And just a huge volume increase in data, but we are also asking a lot more complex questions of the data, and also a lot more, the number of types of questions we are asking is also increasing. So combine all of this, and we just have an exponential demand for compute. To address this compute, there are some major trends underway, which currently are causing a rethink in system architecture. There are three major shifts that we see. First is the rise of object store native architectures. Second is, on one hand, we have object store native architectures, but then we are introducing DB-like capabilities onto these object stores. This is the rise of table formats. And the third trend we see is a new wave of compute engines, often using Arrow at their core. Let's start with the first trend, the great decoupling, the ubiquity of object storage. One of the things we have seen over the last few years is that the dramatic rise of object storage. There's a lot of stuff now you get for free if you use object storage. Firstly, of course, the cost. The economics of object storage is just extremely compelling. Since back in the day when S3 was introduced, the cost of S3 has just gone down almost 10x. Availability of S3, 4 nines, durability with 11 nines, and you get infinite scale. So essentially, if you are a data systems builder, this is a great platform for you to build on top of. A lot of systems, in fact, offload their distributed systems problems to S3. You don't need to, if you are a distributed systems builder, you don't need to worry about consensus, storage, so on and so forth. You just offload the state to S3 and you can dramatically simplify. And Snowflake and Databricks are examples of early movers who understood what was happening, right? If you consider back in 2016 when Snowflake first published their Sigmod paper. Cloud native warehouses and the lake started around then. I think BigQuery was also there. And all of them were exemplars of this underlying notion that what if we could decouple storage and compute? And what if we had our data in object stores? And since then, things have only improved or increased in momentum. We now see every class of system being reimagined on the object store. We have, in fact, in Data Council itself, I think over the last 2 days and even last 2 years of Data Council, we have seen a range of data systems talking about using object store as their core, underlying store. We hear about relational databases who are reimagining themselves using object store, stream engines going diskless, and of course we have the data warehouses and lakehouses. Vector search, I think yesterday Turbo Puffer was talking about how they are using object storage for their vector search solution. So over a period of time, we see that pretty much every class of databases are re-engineering and reimagining themselves to work off object storage. But it's not like lift and shift, right? It's not that you just use object storage and you get everything for free and it's straightforward. There are definitely consequences. For example, in object storage, cost is based on API calls. So if for example in a database you're storing every incoming event as using a separate put, that's going to cost. And if you're going to retrieve it using a get, that's going to cost. So you do have to engineer to take this into consideration. Typically, what engines do is they batch up their requests so that they amortize the cost over multiple events. So you're doing puts and gets on batches. But that has its own consequence, right? And one of those consequences is latency. As it is, S3 or object storage comes with a higher latency than local disk. And now you have batched it up, so then your latencies are just going to increase. So how do you accommodate that? Latency sensitive workloads are definitely going to have some trade-offs to encounter. And of course, you have the consequence of what does it mean in terms of read and write performance. If you want great write performance, you're going to do smaller batches so that you write faster. But if you do that, then your read performance suffers because you have a lot of these small files. That's a very common pattern in databases who are building on top of object storage. And typically what tends to happen is, if you want to trade off between both read and write performance, you will write small batches to optimize for write performance, but then you'll do background compaction so that you get bigger files for read performance. And you do have to worry about things like how do you effectively use caches so that your read performance improves. And if you really want great write performance, you may have to also consider tiered storage where you write to local disk temporarily and then offload it to S3 and stuff like that. So these are all things you have to do to leverage object storage. But if you do this, I think you unlock incredible benefits. The amount of simplicity you gain is amazing. Take WarpStream as an example, right? They were able to re-engineer using object storage. They do have higher latency than Kafka, but the amount of simplicity they were able to unlock, an amount of durability and the resiliency of S3 that they were able to benefit from is incredible. And this is not even considering the more fundamental benefits you get by doing all this, right? Which is you get auto scaling for free because you have almost become stateless, right? If you've offloaded your storage to S3 effectively. So all of this contributes to the rise of data systems reimagining themselves on object storage. But that's just one trend, right? Yes, on one hand, we are doing more and more on object storage, but there are still gaps. And one trend which is addressing some of those gaps is the rise of open table formats. One of the things which you will notice is that over a period of time, broadly what's been happening is we are bringing more and more of database-like capabilities onto object store based systems, onto the lakehouse systems. If you look at the pre-lakehouse era, that is the pre-table format era, when you just had lakes, effectively what existed was object storage as a file system, which is HDFS, and you had the compute, and the middle layer was entirely missing. So what would happen is you would get a range of problems. On one hand, you would have performance-related problems because now you needed to constantly list from your object storage to understand what is there. And on the other hand, you would get all sorts of reliability problems because if you're writing into your object storage and there's some mistake or there was some failure, you've now ended up corrupting the data in object storage. So these were the problems which existed in the pre-table format era. And almost 7-8 years ago, multiple attempts at solving this were started. Iceberg is a great example, Delta, Hoodie, they're all other examples. And their mission was to bring DB-like capabilities to object store. And central to that was the theme of ACID. How do you bring ACID properties onto object store based systems? And along with that, of course, they brought in other stuff like now metadata and table catalogs became important. That was one way for you to avoid having to list and find out what files you have and what data exists in the table. And they also brought in other capabilities which helped in both read and write performance, partitioning, stats, the ability to do schema evaluation, so on and so forth. So what happened was, with this, more and more DB primitives started becoming readily available, right? And that created the onset of the lakehouse era, which is bringing warehouse-like capabilities onto the lake. And more recently, Iceberg for the last 2 years has become very prominent. Increasingly, we are seeing almost everyone support Iceberg. Like S3 tables was a major announcement a few years ago. Snowflake now supports external tables. Kafka made an announcement about TableFlow, which is a very interesting announcement, which is they basically mirror their topics onto Iceberg tables. So you can either consume their events from topics as a stream, or you can scan the underlying Iceberg table. And that sort of seems to plug a very interesting gap which existed, which is, what if you have to reprocess all the data because you want to backfill, or you want to do some sort of evolution in like schema evolution based stuff. So then, instead of processing your events all the way from beginning of time, you can just do a batch job, which is far more optimized for these sort of workloads. Red Panda does the same, and of course we have in the lakehouse itself, multiple engines who can both read and write to Iceberg tables. Now, one of the consequences of this sort of ubiquity is that moment you have everyone using something, it creates its own gravity, right? Like then everyone starts to support it because it becomes easier to interop. So this is starting a new trend or a wave of Iceberg as a almost unit of integration, right? Like applications are now integrating using Iceberg tables. And so this was the second wave, right? Like, so the first wave was more and more systems benefiting from the power of object storage, the infinite durability and scale of object storage. The next wave was bringing in database-like capabilities onto the lake, and the rise of table formats. But we believe that these are not enough in and of themselves, because there are still gaps in what is needed, and therefore we feel there's a third trend, which is a new wave of compute engines. And what are the powerful building blocks which currently exist in the compute engines layer? First, of course, is Arrow. Over the last few years, Arrow has become very ubiquitous. It's become almost the unit of data exchange for data in motion. Just like Iceberg tables for data at rest, Arrow for data in motion, right? And on one hand, you have Arrow. On the other hand, you have Rust Parquet, Apache Data Fusion, Velox, so on and so forth. And these are very interesting because they have built full-fledged tooling, right? Like Data Fusion particularly is a full-fledged stack for building a query engine, a columnar vectorized query engine, right? Now, what these two, I guess, primitives have meant is that it's never been easier to build a simple database. Like literally, there are many people who have, in the order of a few months, built a fully featured engine, right? Like using some of these primitives. And this has in turn led to almost, you could say, an explosion in evolution of databases with different takes on it, different ideas expressed, so on and so forth. So these are fairly powerful building blocks to choose from. So we have object stores, we have open table formats, we have some of these newer engines popping up, but we still have some of these underlying issues, right? Like we have, for example, cost is a common consideration which seems to be there across the board. Like if you take a lot of the existing engines, it's it's still a lot more expensive than it needs to be when you want to perform your workloads. And there remains a huge performance gap in terms of latency, concurrency. Concurrency is a big one. Like as the power of these engines grow, the demand for the workloads also is increasing. People are talking about exposing their dashboards using analytics to end users, right? So then the need for concurrency rises. Now you're no longer talking about tens of QPS, you're talking about hundreds and thousands of QPS. And you want latency and even end-to-end latency. You want events coming in and becoming queryable in the order of seconds. Right now you can't do that. Like it takes many minutes, even with state-of-the-art, best-of-breed sort of solutions, right? And of course, there is vendor lock-in. Like it's hard to change from one engine to another. Like it takes significant effort for an organization to move to a query engine and then, or even an ingest engine, and then shifting from that is non-trivial, right? There's compatibility issues, dialect, significant migration effort, so on and so forth. So to put it all, all the familiar pain points seem to still exist despite all the evolutions which have existed, which have come into fore, right? Ingest latency is still high. We are not able to meet the throughput demands. We talked about how different workloads are reimagining themselves. Take log analytics as an example. It's not unusual to have millions of events throughput in the order of few seconds or minutes, right? Like millions of events per minute is a very non-trivial problem, and that's not something which is currently possible. And query latency, of course, order of sub-second in the order of milliseconds, particularly when you're scanning hundreds of GBs of data, and of course concurrency, thousands of QPS. These are all non-trivial as it stands. So there is a need for innovation. There's a need for some structural changes. Our focus at E6 Data, we believe that if we all are doing the best of breed in terms of what a single executor can do or a single engine can do in terms of columnar, vectorized, use all the latest techniques, so on and so forth, then the unlock has to come from the architecture, right? And one of the things we believe is that to be able to handle the high concurrency sort of requirements, to be able to handle the cost-related considerations, we need to have a fully decentralized, disaggregated architecture which can independently scale and atomically scale. What I mean by atomically scale is, you need to be able to scale extremely fast and extremely granularly. So that's basically the heart of E6 Data's architecture thesis, that fully decentralized, disaggregated, everything's distributed, and atomic scaling. What does it mean? Like if you look at, let's say, some of the existing engines, typically you have highly centralized stateful coordinators with a bunch of workers. The workers tend to scale independently, but the coordinators tend to be a point of contention and sort of set a lower bar in terms of how you can scale effectively. With E6 Data's architecture, we've disaggregated all the various components of the architecture, like the planner, the optimizer, the metadata management, the governance, cache management, so on and so forth. And the idea is that you can independently scale each of these components in a very granular way. And what does that mean? It means if there is a workload increase, then we decide which component needs to scale by how much to accommodate that workload, and just scale those components and by just the minimum needed to accommodate that. So if you go from, let's say, 100 QPS to 110 QPS, you don't need to double up your your landscape, your infra landscape to accommodate it. Maybe just your planner needs to increase by a few cores because it's a plan heavy workload. Or maybe just your metadata management needs to increase, so on and so forth. And here's an example of how that expresses itself. There's This is some sample runs we've done, where as you see the queries per second increasing or decreasing, you see that the number of cores is far more granular than perhaps how other engines may express how they react to that, right? Like we are far more granular and far more atomic in and instantaneous in how we respond to these ups and downs. And this we believe is going to be at the heart of how you control the cost for the increase in workload complexity of the next era. Just like we are reimagining the query engine architecture, we believe even ingest architectures have to be reimagined to be able to handle the sort of requirements we have, which is how do you end up where event comes in and it becomes queryable in the order of 5 seconds or less, and how can you handle millions of events per minute? For these requirements, we have to reimagine the ingest architecture. Like here's an example of how E6 data is architecting its ingest system. We've sort of decomposed what is needed for a typical ingest and making it using arrow batches as a unit of integration. So essentially, as events come in, we batch up into arrow batches, and then it goes through a pipeline which ends in iceberg tables. But there's also parallelized Parquet writer which can scale a lot. But our thesis is, with all this, we can achieve, let's say, a minute or so of ingest latency. But to be able to do 5 seconds, we need a tighter integration of the ingest and the query engine. And our hypothesis is using arrow batches, there's a way to directly integrate the ingest and the query engine to be able to achieve the sub 5 second sort of latencies we are aiming for. So I guess to put it, to summarize, the three trends, object store native, table formats, and reimagining the architectures to be able to decompose arrow native and atomic scaling. Put all these together, we believe is what is needed to be able to handle the requirements of the coming workloads, faster, much lower costs, and being able to handle the sort of concurrency that that workloads demand. This is basically how E6 data is currently positioning itself. Like we've got our real-time ingest engine, which is currently in advanced stages of development, and we've got a compute where we are doing a wide range of use cases. We talked about it earlier, where we saw how different use cases were reimagining themselves on the lakehouse. We are building a vector search currently and log analytics on top, along with, of course, our normal lakehouse analytics, interactive and ad hoc analytics, so on and so forth. We are seeing the impact of that in some of our customers, where we are able to handle thousands of QPS at close to sub 2 second latencies. Cool. On that note, I think we are done. Any questions?